This video was produced by Brunton, Felicia Nasrun, Chan and Rizma Pradhan. We give permission for this video to be shared for educational purposes with other Part 1 engineering students at the University of Auckland. The aim of the first cart experiment was to estimate the mass of the cart and magnetic bumper using the data points we were given. In essence, we want to make comparisons between the calculated solutions that we have analysed and the experimental data that we have been given. So I'll just quickly show a quick run of the actual experiment. Our method involves selecting and analysing appropriate sections of the data that is not influenced by the magnetic force of the bumper, nor the stopper, or any other external forces besides the cable's tension. Once we have determined the appropriate data points to use, we can use this information to estimate the total combined mass of the cart and bumper, while assuming that we are calculating the acceleration of the cart that is solely caused by the action of the 30-gram mass. Now, with these assumptions, we then created an acceleration versus time curve and compared it to our experimental data. And we continued constructing velocity versus time, as well as displacement versus time profiles, and comparing these integrated results with measured results. Here are the free body diagrams of the 30-gram mass and the cart with their coordinate system, whereby positive motion in the y direction is downwards, as this 30-gram mass accelerates downwards, and the positive x direction is towards the left, as the acceleration of this 30-gram mass causes the cart to accelerate towards the left. Cuts have been made, indicated by these dashed lines, so that we can construct free body diagrams for the known mass of 30 grams and our unknown cart and bumper mass. The kinematic constraints and assumptions include the pulley is of very low friction and lightweight, so that we don't have to consider the mass moment of inertia of this pulley, and the acceleration of the cart in the y direction is equal to 0, so that we're assuming that the acceleration of the cart only occurs in the x direction. And finally, the acceleration of the cart in the x direction is equal to the acceleration of the 30-gram mass in the y direction due to the existence of this pulley, so that the tension forces are equal. And so in this next slide, we have selected appropriate sections of the data that are not influenced by the repelling magnetic force or any other forces apart from the tension of the cable, in order to calculate the average acceleration of the cart. These sections included the acceleration values obtained as the cart was accelerating to the left prior to it being affected by the interaction of the magnets, named Section 1, and Section 2 included when the cart has bounced away and was accelerating back again towards the stopper. We obtained the same overall average acceleration of 0.962 meters per second squared. Using the average acceleration we have obtained, we can assume that this is equal to the acceleration of the cart in the x direction and the acceleration of the 30-gram mass in the y direction. When we take sum of forces in the y direction, we get that mg minus t is equal to ma, so that rearranging and solving for t gives us a tension force of 0.27 newtons. As we indicated earlier in our free body diagrams, the tension force of the 30-gram mass and the cart is the same due to the pulley system. So we can take the sum of forces in the x direction for the cart, make it equal to ma, to find the total combined mass of the cart and bumper, which was found to be 276 grams. Here we have selected appropriate sections of the data again in order to calculate the average force applied by the bumper to the cart, as detected by the force sensor. After calculations, we decided to exclude the force readings in Run 1 Section 2, as the readings were much higher than expected, and this may be due to the magnetic bumper and stopper repelling each other, producing a greater combined force. We then used the average force readings to estimate the mass of the bumper and the cart, and we obtained slightly different values for Runs 1 and 2. But what we can conclude here was that the mass of the bumper was around 30 grams and the mass of the cart itself was around 240 to 250 grams. Comparing analytical versus measured data, we have made the assumption that the acceleration of the cart and bumper is constant all the way through, giving us a linear horizontal line in the acceleration versus time graph. Integrating this gave us a linear positive slope for the velocity time graph, and integrating this further gave us a parabolic shaped displacement versus time graph with the equation 0.481 multiplied by t squared. When we compare acceleration data with the sections in Runs 1 and 2, we can see that experimentally, acceleration was not always constant, and over time, it actually starts to decrease slightly in all these four graphs, and this is likely related to the assumptions that we have made when calculating acceleration. In practical settings, due to the slight decrease in acceleration of the cart over time, the measured velocity values never quite reaches the calculated theoretical value, and this is particularly obvious in Section 1 of Runs 1 and 2. Whereby we see a greater gap between analytical and experimental data compared to Section 2. However, it is also evident that the general trends of calculated versus measured data in all four graphs will very similarly positive linear slope. Finally, for the displacement versus time profiles, we see identical parabolic trends for both calculated and measured data. The only subtle differences would be in the absolute final displacement attained at 1 second, whereby the calculated value was slightly higher than that obtained experimentally. Again, this might have been caused by the higher velocity in the analytical data compared to the measured, therefore taking a shorter amount of time in order to reach the same point. To conclude, our estimated bumper mass was around 30 grams and estimated cart mass was around 250 grams, giving a total combined mass of approximately 280 grams. Our theoretical calculated data differed from our measured data in that acceleration never remained constant experimentally due to factors such as air resistance and friction coming into play. Hence, integrating a constant acceleration resulted in velocity values that were generally higher than values obtained experimentally. Further integration results in displacement values that slightly differed between predicted and actual values. However, the theoretical and experimental velocity versus time and displacement versus time profiles had the same linear and parabolic trends, although the individual values differed slightly. These differences were probably due to the assumptions and kinematic constraints that we have made when performing calculations.
For our second experiment, we decided to explore the topics of kinematics of particles and friction. We came up with the concept of a pulley system connected to a mass, and finding the mass required to produce an acceleration great enough to prevent a slipping object that is connected to the other end of the pulley from slipping. The mass of the slipping object would be known, as well as the coefficient of friction, which could be found from tan the slope's angle, and we would need to find the mass of object B to create an acceleration great enough to prevent object A from slipping on the skateboard. To find the mass of object B, we must first find the acceleration at which it takes for object A to stop slipping. So we must first draw a free body diagram of the sliding object and the skateboard with an appropriate coordinate system as shown. The kinematic constraints we have are acceleration in the y direction equals to 0, and we assume that the wheels are lightweight and frictionless. And we also assume the pulley to be lightweight and frictionless as well. This means that the sum of forces in the y direction equals to 0. Hence, sum of forces in the y direction equals normal force sine 72 plus the force of friction sine 18 minus the mass of the object times gravity equating to 0. Since we know that the force of friction equates to 0.32 times the normal force, we can substitute friction into the sum of forces in the y direction equation. This leaves us with this equation. By rearranging and solving for n, it gives us a value of 0.83 newtons. We then take sum of forces in the x direction and we end up with the equation of normal force cos 72 minus force of friction cos 18 equating to the mass of object A times acceleration x. By rearranging the terms for ax, then substituting and solving, we find the acceleration in the x direction to be 0.054 meters per second squared. Now that we have the acceleration, we can use this to find the mass of object B needed to produce this acceleration. To do this, we draw another two separate free body diagrams as shown. With the skateboard's free body diagram, we can form an equation using sum of forces in the x direction. This gives us this equation. The second equation that's needed to find the mass of object B can be found using sum of forces in the y direction. As there's only the forces of T and mg acting in the y direction, the second equation becomes this. We can rearrange for T, leaving us with the equation T equals to mass times the mass of B times gravity minus acceleration in the y direction. As we know that both equations 1 and 2 have T in common, we can equate those two equations. And since acceleration in the y in the skateboard's free body diagram equals to 0, and acceleration in the x direction in object B's free body diagram equals to 0, we can assume that acceleration in the x direction of the skateboard equals acceleration in the y direction for object B. With this in mind, we can rearrange for the mass of object B and solve. This leaves us with mass of object B equating to 0.01728 kg, or 17.28 grams. This is the mass that's needed to produce an acceleration great enough to stop the object A from slipping. As shown in the video, 17.28 grams was not enough to create an acceleration large enough to prevent object A from slipping. So we continued to increase the mass of object B until we found the mass needed. We found that the mass of object B was much larger than expected. This may be due to the fact that in our physical world, we're unable to assume the wheels and the pulley to be lightweight and frictionless. Also, as the skateboard is quite old and the bearings haven't been oiled for quite some time, it might have been harder for the wheels to turn. The distribution of mass of the wheels would also have an effect. Since most of the mass is concentrated in the center, object B would need to increase its mass to overcome the rotational inertia.